Hey folks, welcome to this episode on mole conversions, talking about particles to atoms and atoms to particles. So again, we've been working on this little chart here, and we see that we are able to go from moles into particles. Particles being atoms, molecules, or formula units. Now, we can go directly from molecules into these particles if they are talking about the same thing. So for example, if I had ZnCl2 and I was asked to find out how many molecules, or in this case formula units, this is formula units because it's a metal and non-metal, I can go from here into formula units of ZnCl2 just by using Avogadro's constant. However, if I was given moles and I was asked to go into atoms of Cl, I couldn't directly go there because I first have to figure out how many formula units there are in this many moles, and then my next step would be to figure out how many atoms of Cl there are. So this is what we're going to be doing right now. We're going to be going from these particles to these atoms. Now, again, if we're given moles of something like gold that exists as an atom already, and we're trying to figure out atoms, well, that's a straight shot. All we have to do is that. But if we're given a compound and we're being asked for an atom, we first have to go into this particle and then find out how many atoms. Same thing, if we're given atoms and we're asked to find moles of a compound, we first have to figure out how many molecules or formula units there are, and then go into moles. So, let's try to create a definition for this molecule. Here we have NH3, we have one nitrogen, three hydrogens, and this beautiful little lone pair there on the nitrogen. So when it comes to this molecule, this is a standard ammonia molecule, and if I looked in China, or I looked in Poland, or I looked in Belgium, or in Canada, or the US, ammonia molecule would be the same thing, NH3. So in this molecule of ammonia, how many hydrogen atoms are there? Well, it's simple. We can just count. There are 3 hydrogen atoms for every 1 molecule of ammonia. So 1 molecule of NH3 contains 3 atoms of hydrogen. We have just created a constant, and we're going to be using this constant to help with our conversions from particles, which in this case is a molecule, to atoms, here atoms of hydrogen. Now we can do the same kind of definition for atoms of nitrogen in 1 molecule of ammonia, and again we can just count that. Here we have 1 atom of nitrogen in for every 1 molecule of ammonia. So in this case, 1 atom of nitrogen for every 1 molecule of NH3. So what's important to see is that it doesn't really matter which order it is. What we're creating here is a little ratio and a relationship. So let's try to employ these definitions into an actual question. It says how many hydrogen atoms would you have if you had 100 molecules of ammonia? So in this case I have 100 molecules of NH3. Now I'm going to use a dimensional analysis. So I want to get rid of my unit molecules of NH3. And because I'm talking about molecules and atoms, there actually is a direct relationship. Here's a molecule, here are atoms. So I can figure out how many atoms there are of hydrogen directly. Now, what is my definition here? What's my relationship between atoms of hydrogen and molecules of ammonia? Well, I already established it right over here. 1 molecule of ammonia gives me 3 atoms of hydrogen. 1, 3. So my units will cancel out. 100 times 3 gives us 300 atoms of hydrogen. So what this means is that if I had 100 molecules of ammonia, those 100 molecules of ammonia would contain 300 atoms of hydrogen. Now let's do this one over here. We have 6.02 times 10 to the 23 molecules of NH3. Now again, I want to get rid of molecules of NH3, so I put that on the bottom, and I want to figure out how many atoms of hydrogen there are. Now again, we've already established this. There is 3 hydrogen atoms for every 1 molecule of ammonia. That standard doesn't change. That is a constant. And so again, my units will cancel out, and I'll be left with 1.81 times 10 to the power of 24 atoms of hydrogen. So let's actually do a question here. It says, how many atoms of oxygen are in 763 molecules of diphosphorus pentoxide? Now, to do this, we have to create that constant again. And that constant, when we're talking about molecules, all depends on the molecule and the atom that you're being asked for. So in this case, here we have diphosphorus pentoxide. The formula for that is P2O5. So this is one molecule. Again, it's a molecule because these are non-metals together. How many atoms of each are in this molecule? Well, I have 2 phosphorus atoms and I have 5 oxygen atoms. So here I've actually just created a definition. One molecule of P2O5 gives me 5 atoms of oxygen. One molecule of P2O5 equals 5 atoms of oxygen. So here is my constant. Now, I don't necessarily have to write it out like this every single time, but it's nice to visualize and kind of come back to when we're actually doing this equation. So again, I'm going to underline what I'm given, 763 molecules of diphosphorus pentoxide, and I'm looking for atoms of oxygen. So let's start by writing out what we have. 763 molecules of P2O5. Now I want to get rid of this, so I'm going to put molecules of P2O5 on the bottom, and I want to be left with atoms of oxygen. So again, what is my relationship between atoms of oxygen and molecules of P2O5? Well, we've established it here and here. For every one molecule, I have 5 atoms of oxygen. Perfect. So let's cancel out our units, and here we're going to multiply these two values together. And when I do that and I round for 3 significant digits, what I get is 3.82 times 10 to the power of 3 atoms of oxygen. So that means that there's 3.82 times 10 to the 3 atoms of oxygen in this sample of 763 molecules of P2O5. All right, so take a look at these questions here. And the first question is dealing with ethane, C2H6. We have this many ethane molecules, and we're looking for atoms of carbon that make up the sample. The second one is a really interesting one. Here we have a glass of water that contains 10 moles of water, and we're being asked to find out atoms of hydrogen. So we're given moles of water and being asked for atoms of hydrogen. These are not the same particle types. This is a molecule, H2O. This is an atom, just H. There's no direct way of going from molecules to atoms. What we're going to have to do from moles of H2O is we're going to have to go into something first, and then from finding that, then we can go into atoms of hydrogen. So I'm going to leave that up to you. Try to figure out what this thing we have to convert to is first, and then go into atoms of hydrogen. So pause the video, really think about it, and then try your hand at it. We'll come back with the answers. So go ahead, pause the video now. Okay, so as expected, the first one is pretty simple. Here we had molecules of ethane. We want to get rid of our molecules of C2H6, so we put that on the bottom. And for every molecule of ethane, we had 2 atoms of carbon. So we just took this number, multiplied it by 2, and got our final answer. The second one, however, we couldn't go directly from mole to atoms. What we had to do was go from mole of H2O into molecules of H2O. Okay, so that was our first lesson in conversions, going from mole to molecules. And we did that by multiplying by Avogadro's constant. Our mole of H2O canceled out, and we're left with molecules of H2O. After we figure out how many molecules of H2O we had, we could then, this is just the same number, just written over, we can then figure out how many atoms of hydrogen there are for every molecule of H2O. So again, our molecules of H2O will cancel out by putting it on the denominator, and there are 2 atoms of hydrogen for every 1 molecule of H2O. So we take this number, multiply by 2, 3 significant figures. There is our answer. All right, now let's go the opposite way. Here we have Na3PO4, sodium phosphate, and this is a formula unit because, again, this is a metal and a non-metal set of polyatomic ions. Well, not ions, but polyatomic ion. This is phosphate. So this is a cation, this is an anion together that forms an ionic compound, and those are called formula units. So we have this formula unit of sodium phosphate, and there are 2.55 times 10 to the 24 ions of sodium present in the sample. Okay, so it's talking about ions of sodium, and we are given a formula unit. It's asking us how many molecules or how many formula units of this sodium phosphate does this equate to. Okay, so in this case, they're using molecules in this kind of quotations, but this should really be talking about formula units because sodium phosphate is an ionic compound. So how many formula units are in this sample of ions? So let's first figure out what is going on here. We have Na3PO4. Now, when we break this down, we get how many ions of sodium? We actually get 3 Na plus. This is kind of like our ionic equations, where we take aqueous, and this is, it says aqueous there, so we can actually break it up into ions. And we have 3 Na aqueous, and we only have 1 PO4 3 minus aqueous ion. Okay, so in this one formula unit right here, this one formula unit of sodium phosphate, we have 3 ions of sodium and 1 phosphate ion here. So what we've just done is, again, we've created a definition for us to use right here. One formula unit of sodium phosphate equals 3 ions of sodium. So let's try to work this into this example. So here we have 2.55 times 10 to the power of 24 ions of Na plus. All right, now we want to try to figure out molecules of sodium phosphate. So I want to get rid of this unit ions of Na plus, so I'm going to put that on the bottom, and I want to be left with F units of Na3PO4, formula units of Na3PO4. Now, what is my relationship between formula units of Na3PO4 and ions of sodium? It's right over here. One formula unit of sodium phosphate equals 3 ions of sodium. So I'm going to put that over here, 1 and 3. So effectively what I'm doing is I'm taking this number, dividing it by 3, and my units cancel out. And what I get here is I get 8.5 times 10 to the 23 formula units of Na3PO4. All right, so once again, try your hand at these questions. The first one's talking about fructose, which has a very similar or the same formula for glucose. And it's asking us how many fructose molecules does this equate to. So again, we're looking at the relationship between atoms of oxygen and fructose molecules. And the second one, here we have a can of Diet Coke that contains aspartame. Here's the formula for aspartame. And it contained 7.366 times 10 to the 20 atoms of nitrogen. So here is our molecule, and it's contained this many atoms of nitrogen. How many moles? How many moles of aspartame are found in this Diet Coke? So we were given atoms of nitrogen, and we're trying to find out moles of this aspartame. Can we go there directly? So that's something that you need to think about. Once you figure that out, maybe create a little game plan saying this, I need to go into this, etc., etc., and follow that game plan using your numbers to come up with the final answer. So pause the video, really work on it, really think about this. Can we go from atoms of nitrogen directly into moles of aspartame, or is there maybe something in between? Try to work on it. We'll come back with the answers in a short moment. So go ahead, pause the video now. Alrighty, welcome back. So again, the first one's pretty obvious. We can go from atoms into molecules by looking at that relationship. For one molecule of fructose, we have 6 atoms of oxygen, and that's just given to you by the formula here. So our atoms of oxygen will cancel out, and we'll be left with molecules of fructose. The second one, I hope you got my hint. There's not a possible way to go from atoms into moles directly. We first need to go into molecules of aspartame, and that's again by looking at the relationship between atoms of nitrogen. Here's 2 atoms of nitrogen for every molecule of aspartame. So we use that relationship to get how many molecules we have. And once we have that, we can just rewrite our number here. And what's the relationship between molecules and moles? Well, mole, molecule, molecule, mole, molecule. It's mole and particles. What's the relationship between mole and particles? Remember, 1 mole is equal to 6.022 times 10 to the 23 of whatever you're measuring. So that 6.022 times 10 to the 23 is measuring molecules. That goes on the bottom. And you're effectively dividing. Your units will cancel out, and you'll get your answer, 6.116 times 10 to the negative 4 moles. All right, so here what we've done is we've gone through this little part of the chart. Again, if you're given moles of a compound, you can't go directly into atoms of whatever of those elements in that compound. You first have to figure out how many molecules or formulas you have, and then go into atoms. If you're given something like Cu, which is already in atom form, you can go directly into atoms through this way here. So here's some mixed practice. Take a few moments, work through it, use your dimensional analysis, use your units, let your units guide you. We'll come back and show you the answers for these. So go ahead and pause the video now, really work, really struggle, try to get through all of them. All right, pause the video, we'll come back. So here are your answers. The first one is a two-step procedure because we are given atoms. We're given atoms of Cl, and we're asking for moles of NCl3. So again, we're going from atoms into moles. There's not a direct way when we're dealing with atoms here, and moles of a compound. So we first have to figure out how many molecules we have of NCl3. Again, this is a molecule because these are nonmetals. Once we did that, we can go into moles using Avogadro's constant. This is very simple. Here we have moles of Ag, and we can go directly into atoms of Ag because it's the same species, Ag and Ag. So we can just use Avogadro's constant to get there. The third one here, it says jug of methanol. So again, we're looking at moles of a molecule, CH3OH, and we're being asked for atoms of oxygen. Again, we can't go from moles of a molecule to atoms of the elements in that molecule. We first have to figure out how many molecules we have, and then figure out how many atoms we have. Finally, the last one, here we have ions of H+, and we want to figure out how many moles of hydrogen there are. Well, it's the same species, H+ ions and moles of H+ ions, so we can just go directly using that one step. Alright folks, that's it for now. Thanks very much for watching. We'll see you soon.